Before we get too deep into triple integrals using the spherical coordinate system, I'm going to use this little video to help break down a few equations that aren't too difficult to work with if they were converted to spherical coordinates. So this first example is z equals 2, so it's the equation of a plane. So you might be able to see from the 3D image that's shown here, that plane that's kind of a light blue color is floating 2 units above the xy plane. So what we have here is, let's get it marked out here. So that's y, and that's the x-axis, so the z-axis up here. So that plane's there. So as I mentioned in class, one of the important aspects, if you struggle seeing things in 3 dimensions, is to be able to look at it from a particular angle. And in spherical coordinates, I'll tell you right now, the side view is particularly useful. One of the reasons it will be useful, but not on this video, is that the angle phi makes works with the positive z-axis. So you can see here that the z-axis is highlighted. So z equals 2 is a horizontal plane, but in this particular picture, it kind of just looks like a horizontal line. I mean, that's it right there. I'm decorating over the top of it. So how would we make the conversion? Well, the goal is to write an equation in terms of rho equals. And what we have here is that z equals 2. And we know from our list of formulas that z is equal to rho cosine of the angle phi. So if we're going to solve this for rho equals, make a little space here, we'd have rho equals either 2 divided by cosine of phi or 2 secant of phi. That would be the spherical version of that horizontal plane, which could become a boundary in some 3D graph in a triple integral. There's the first example. Let's just slide her up a little bit here. So next example is has the algebraic equation x squared plus y squared equals 4. So let me ask, what is that graph? No, you might be wrong this time. If you were looking at this in 2 dimensions, then that would definitely be the circle that some of you were thinking about. But if this is a surface, then in 3 dimensions, this is what we've defined earlier this semester as a cylinder. And this particular cylinder really does look like a cylinder. It's going to be a circle that extends forever in the 3rd dimension, which in this case is z. So let me just slide the image up here a little bit here. I've got a picture for us to play with. And let's go up a little bit further. All right, so you can see here there's the cylinder. The radius of that cylinder is indeed 2 units. So this point right here is 2 units out, and this point here is 2 units out. And that is the y-axis, and that is the x-axis, and the z-axis is up here. So that cylinder in 3 dimensions, from the side view, you just see this line in the, if we were looking at the first octant. So there's the z-axis, here's the z-axis, and here's your line 2 units out. So if we were in the first octant where all values are positive, we might be looking at literally a cylinder. You know, who knows how tall the cylinder is. I'll just put just a non-specific top line out right there. So how do we write the equation of that 3-dimensional cylinder? Well, we know that, as I slide some more space here, we have x squared plus y squared equals 4. And so that means that r squared is 4, or therefore that r equals 2. And if we look at our list of spherical conversions, we'll find out that r is equal to rho times the sine of phi. So to get the spherical equation for that cylinder, we would say rho equals 2 divided by sine of phi, which is 2 cosecant of phi. So there's a second type of graph, not difficult to look at. We've looked at it in rectangular and polar and cylindrical coordinates with triple integrals. So let me show you one more that's just a little bit different. Not hard to imagine, but not one you're going to hope to get too many of. So what do you think this algebra here represents? It is something we have seen in our past. Yeah, that's right. It is a sphere. It has a radius that is 1 unit. And this particular sphere, not fear, a little Freudian slip there, has a center 0, 0, 1, so 1 unit up on the z-axis. So I happen to have a sketch of it right here. There we go. So this sphere is centered 1 unit up on the z-axis. Let's find a color that maybe stands out better. And extends 2 units above. And there's your x-axis and your y-axis here. So we're going to convert this to a spherical equation. I'll just point out to you that we know that x squared plus y squared plus z minus 1 squared equals 1. We can use a few not too difficult algebra properties to rewrite this. Minus 2z plus 1 equals 1. And in our list of spherical conversions, x squared plus y squared plus z squared is actually equal to rho squared minus 2z. Z is rho cosine of phi, and if we subtract 1 from both sides we get 0. And if we do a little addition and then division, we would end up with the fact that rho equals 2 cosine of phi. So I'm going to leave you with this little challenge. That is the spherical equation for the sphere you can see here. What angles of phi do you think might be used in tracing that graph? And what values of theta might be used in tracing that graph? When we set up our spherical integral, that's something we're going to want to know. All right, signing off for now.